Okay, so I'm just going to wait until the chat room populates. If not, I'll just do the lesson by myself and then you can watch it later. Hi, Redbeck. Hi, Caroline. Can you hear me okay? Thank you. Hi, Juan. You have to complete the assignment online, and WebAssign grades it for you and then sends me the scores. So it's due by the next class period. I think it closes out at, I want to say 11, maybe 12 on Wednesday. Does that make sense? Oh, are you talking about the should I ask you guys? I can't get into ESB right now. I did pose a question, but I thought it was for you guys to get feedback about what topics. All you have to do is reply and tell me what topic you want to know more about or that you struggle with, and I'll make sure I include it as part of the review. Hi, Indu. You know what? I bought this new computer over spring break because I had the black screen of death, and it automatically hooked up to the internet, so I never thought to connect a wire. So Spectrum thought I was pretty stupid when I called and asked them what port that I needed to put the wire in and everything. Hi, Charlie. So we're all set now, thanks to you guys. Well, actually, there was that one student. I'd have to look back at the other chat on what his name was, but I think he was the one who brought it to my attention that I needed a LAN. I'm going to start in just a minute. Okay. Let me just get out of here and we're going to begin. Okay. Exit. All right, so let's start. Okay, Taylor polynomials. Yeah, I'm noticing that one. I had no idea. So for like 2 weeks, I've been using my computer on wireless. Yes, Charlie, that's the only current one. So every time we have a lesson, I'll open up an assignment for you guys to do some work from that topic. I'm not going to inundate you. I will start giving you FRQs from AP. So in other words, today, after my 3 o'clock meeting, I have some FRQs that I need to cut and paste and I'll probably post them to EDSB if I can get in. So you guys can also get some FRQ practice as well, and then we can go over them in the next class. Okay, so what are we going to do? I already discussed the objectives. We're going to find Taylor and Mclaren polynomials. We're going to review the big five polynomials, and we're going to find nth degree polynomials that we're going to use to approximate a function. Okay, so I know the last video was pretty bad, so I'm just going to go back over this, and I apologize for the redundancy. So the big idea, we have difficult functions, and we're going to use easy polynomials to approximate those difficult functions at some center C. So it's in an interval with a center that we call C. And it's x minus the center equals to 0. So at the point where x is equal to C, that's the center we're looking for. So if it's Mclaren, the center will always be 0. And if it's Taylor, it'll be some other number. Okay, so just don't forget, like I mentioned many times, that if you're asked to find, a fifth degree Mclaren polynomial or something with the word Mclaren in it, then that means your center is 0, because they're banking on you forgetting that fact. They're going to test to see if you know what that is. So don't be like when you're taking the test, oh my God, they didn't give me the center. If the word Mclaren's in there, the center's 0, right? So the formulas. This is Taylor's formula. Okay, the nth degree polynomial is equal to the nth derivative of f at the point where x equals to c times x minus c to the n over n factorial. And again, this looks ugly, but this thing that I had circled earlier, this is a coefficient. So it's this times x to the something, okay? So this is just going to be a number here. And if you're dealing with Mclaren, well, the formula collapses down a little bit pretty nicely, because if I plug a 0 into that big formula, x minus 0 is just x. So you're going to end up with your coefficient times x to the n, okay? So we always start out with Mclaren because they're nice and easy to calculate, and then we work up to adding some other centers and representing the functions with the Taylor polynomial. Okay, so once again in the little key, P stands for polynomial, n is the degree of the polynomial. This nth derivative at c, that's exactly what it means. And this, again, is going to be the coefficient of each term in the polynomial. So what I started out with last time is this general form. So let's pretend we're going to approximate some function f, I don't know what it is, by this polynomial. This is just a general polynomial. And just remember that when we write polynomials in higher math, we always start with the constant and then we work our way up. So you can see that the powers on x are in ascending order. And I'm calling this equation 1 because we're going to use it later on down the line. Okay, and we have to have two assumptions here. The first one is that the first n derivatives exist. So in other words, we've got to be able to take 5 derivatives if we need a fifth degree polynomial. So the derivatives have to exist. And then the other thing we need to assume is that the polynomial and its first n derivatives have to match the function and its first n derivatives. So what that means is that if I evaluate the function f when x is equal to 0, let's say, and I evaluate the polynomial when x is equal to 0, the two would be equal at that point, or at that center. Likewise, if I evaluate the function's first derivative at 0 and the polynomial's first derivative at 0, it's going to match, okay? So I'm calling this number 2 because we're going to use this again too pretty soon. So far, so good, right? If not, just don't hesitate to ask me a question. Okay, so here's the important part. So what we're doing is we're building this polynomial, or sorry, this formula for the polynomial. So here's our polynomial, our general polynomial, okay? And if we take the first derivative of that polynomial, well, this goes away, right? Derivative constant 0. And then using the power rule for each term, we get a sub 1. Taking the derivative of this, we get 2a sub 2x, 3a sub 3x squared, and so forth. And then here in this general term, and I don't want you to forget this because this is really important, this is called the general term. This is the term that will generate every term in the polynomial. So when we get to the general term, we're going to still use the power rule, right? And bring in the n down, right? So it's n times a to the a sub n, which this is just some number, times x to the n minus 1, because we subtract 1 when we take the derivative. And if I take the second derivative, well, the derivative of this is 0. The derivative of this is just 2a sub 2, because the derivative of x is 1, so we're left with this term. The derivative here is 2 times 3, or 6, a sub 3x squared, so I've got that here. Now we would keep doing that for every term, and then for the general term, we're going to bring this n minus 1 down, so we have n times n minus 1, a sub n, x to the n minus 2. And we keep repeating this process until we get to the nth term. And the nth polynomial, or the polynomial of degree n, what's going to happen is, if you do enough of these, you're going to see that all of these constants are going to go away and this thing's sort of shifting. Well, what you're going to see is that we're going to end up with this factorial, which is really just n factorial here, right? n minus 1, n minus 2, all the way down to 1 times that coefficient a sub n. So if we can do that, then what we can say is, if I plug a 0 in to p, all of this stuff's going to cancel. I'm going to be left with a 0, right? This is going to be a 0, and be left with a sub naught. If I plug a 0 into here, so remember, I'm plugging the 0 in for x. Anything here is going to cancel out. What I'm going to be left with is just a sub 1. If I plug a 0 into p double prime, all of this is going to go away, and I'm going to be left with 2a sub 2. And what I did was I wrote 2 as 2 factorial, so you could see a pattern. Likewise with p triple prime, all of this is going to go away, and we're going to be left with 6a sub 3. And we can write 6 as 3 factorial, right? 3 times 2 times 1 times that this coefficient here, a sub 3. And then we keep doing that and doing that and doing that. And finally, when I plug a 0 into here, well, now there's no x's to plug the 0 into. So what I'm left with is n factorial times a sub n. Are we okay so far? Any questions so far? Going too fast, too slow? Are y'all taking a nap or something? Because nobody's responding. The factorial, where did it come from? So which factorial? Are we talking about this factorial, that factorial? Was it the 2 factorial, the 3 factorial that you're wondering? Okay, so look, the number 2 is a 2, right? But we also know that 2 factorial is equal to 2 times 1, which is 2. So I just wrote this as, you could leave it as a 2 if you wanted to. I wrote it as 2 factorial because I want to show you a pattern in a minute. Likewise with the number 6, I know that 3 times 2 times 1 is equal to 6. So I'm replacing the 6 with the 3 factorial. Again, nothing more than to show you a pattern. Now, n factorial, by definition, right, is n times n minus 1 times n minus 2 times n minus 3 times times 3 times 2 times 1. Oops. Okay, so just like with the number 6, it's 3 times 2 times 1. So with a factorial, we start out, with the biggest number and we work our way all the way down. Well, that's what's happening here. I have n times n minus 1 times n minus 2. If I generated another term, it would be times n minus 3 times n minus 4, and on and on and on, all the way down till we got to 3, 2, 1 times whatever number it's being multiplied to. Is that okay? So I'm just rewriting it 6 is the same as 3 factorial. I'm just putting it in factorial form to show you something in a few minutes. Is that all right? But I didn't have to, so you don't have to either. Okay, so with these things established, what we learned, remember, in equation 2 is that if I plug the 0 into f, it had to be equal to p of 0. And if I plug the 0 into f prime, it would have to be equal to plugging the 0 into p prime, right? So using that idea, and let me just bring it back up here again to show you. Okay, so this was equation 2, or statement 2, is that for every derivative I take, if I plug my center in, each one should be equal to its corresponding polynomial, right? They have to match, all right? So keep that idea in mind. So all I'm doing is, let's see if I can put these side by side. Can I fit them? See, on my screen, everything's kind of backwards, so just bear with me a second. Sorry about it. And my new computer legs are, I'm going to move my camera, kind of in the way too. Okay, so here's statement 2 right here. Okay, and here's what I'm doing. I'm saying that if f of 0 has to equal to p of 0, well, when we plugged the 0 into p, we got a sub naught. So I'm saying this is equal to a sub naught, because that's what p of 0 is. And then I'm going to this one, and I'm saying, well, if I plug the 0 into the derivative of p, it has to equal f prime of 0. So automatically I'm saying f prime of 0 equals p prime of 0. Well, p prime of 0 was a sub 1. So I'm jotting that down there. F double prime of 0 has to equal to p double prime of 0. So that means that f double prime of 0 must equal to p double prime of 0, which is 2 factorial a sub 2. And finally, well, not finally, but the jerk at 0 has to equal to the third derivative, or the jerk of p at 0. And p triple prime of 0 is 3 factorial a sub 3. So I'm just filling in this side of the column based on this statement number 2 over here. And if I go to the nth term, the nth derivative, then if I plug a 0 in there, it should equal the polynomials, the nth derivative of the polynomial at 0. Well, the nth derivative of the polynomial at 0 was n factorial times a sub n. Okay, now for these three, because they had a little bit more stuff going on in them, my goal is to solve for a naught, a sub 1, a sub 2, a sub 3, and a sub n. So all I'm doing here is showing you that if I divide both sides by 2 factorial, then a sub 2 is equal to this. And in this one, if I divide both sides by 3 factorial, then a sub 3 is equal to this. And then the final term, the nth term, if I divide both sides by n factorial, then a sub n equals to that. Okay. Now remember our original polynomial, our general polynomial. It's right here. This was the first equation I wrote down or numbered as 1. What I'm going to do now is I'm going to replace this a naught, a sub 1, a sub 2, and so forth with these things I found here. Okay, so what do I know? I know that a sub naught is equal to f of 0. And I just threw a 0 factorial under there because 0 factorial is equal to 1. All right, so again, you don't have to write that often. We don't write it, but again, I'm trying to show you a pattern. Okay, so just bear with me. Now here, I need to do a sub 1 times x. Well, a sub 1 is f prime of 0, so I'm replacing this a sub 1 with f prime of 0. There's my x. Here's my x here, and this is x to the first power, so I put it over 1 factorial. In this one here, I'm replacing a sub 2. Well, a sub 2 is this whole mess here. It's f double prime of 0 over 2 factorial times x squared. A sub 3, so now I'm going to replace this one. Well, that's f triple prime of 0 over 3 factorial times x cubed plus da 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 da. And then finally, for the last, or the nth term, I'm replacing a sub n, which is the nth derivative of 0 over n factorial times x sub n. Okay, so what I'm doing is I'm doing all this work to replace these coefficients in this polynomial with these things. And what that does is it gives us the formula for Mclaren polynomial, okay? Because we say that this nth degree polynomial is just equal to, so what I'm trying to get you to see with this pattern here thing is that, you know, this is x to the 0 over 0 factorial. This is x to the 1 over 1 factorial. This is x squared, so that's 2 factorial. So in other words, the powers or degrees on x match the factorial below it, okay? If I have, you know, x to the 6, I would expect a 6 factorial below, and so forth. Okay, so again, you don't have to do the 0, the 1 factorial. You don't have to write a 6 as a 3 factorial if you don't want to. But you can see here that this pattern is important because you have to know this formula by heart, so it'll help you generate these polynomials very, very quickly. So the general formula for this Mclaren polynomial is f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 x cubed over 3 factorial plus the fourth derivative of 0 x to the fourth over 4 factorial, and on and on and on, all the way till we get back to this general term. And that's the definition for the nth Mclaren polynomial for the function f. Taylor would be the same thing, except instead of a 0 here, you would have some other number, and then it starts to really look ugly, but it's not hard. It's just, it's easy. It just looks worse. So we're going to do some in a minute. Okay, but the nice thing is if you remember the formula, because remember, AP is not going to give you formulae. It's not going to tell you what the formula is. If you can remember the formula, and you will, then you just have to do really a couple of steps. You're not building the polynomial. You're not trying to derive it. What you're trying to do is use it. Okay, so what you're going to do is you're going to be given a function, and you may be asked to find the fourth degree Mclaren polynomial, let's say. So that means you need to take 4 derivatives. You always write the original function first. That's the 0th derivative. So you write the original function and all the derivatives you need, okay? And you write them down in a column, as you're going to see me do and as you've seen me do before. And then you're going to evaluate the original function in each one of those derivatives that you found at the point of interest, so at the center that they want. So in this case, we're talking about Mclaren, so our center is 0. Okay? And that's going to generate the coefficients of each term in your polynomial. And then what you're going to do is you're going to substitute those things into this general form. Okay, so let's look at e to the x. And let me just get some extra paper here in case I need it. And my calculator, because I want to show you a visual on that. Okay. So remember, we're trying to find these nth degree polynomials that are going to help us approximate some ridiculous function, okay? The most basic is e to the x, okay? And they want you to find the Mclaren polynomials, p sub naught, p sub 1, 2, 3, and p sub n. So what am I going to do? I'm going to follow the steps that I wrote, okay? I'm going to write down the original function, and I just put a little note here. This is the 0th derivative, so it's just f of x. There's no derivatives, the original function, okay? So the original function was e to the x. So look, I want to go all the way up to the nth polynomial here. So I need at least 3 derivatives that I can see, and then the nth one. So I write down the original. I take the first derivative, second derivative, the third derivative, and I can stop there. If they wanted p sub 4, I would take 1 more, which would still be e to the x, and then I have to take the nth derivative. Well, the nth derivative of e to the x is still e to the x. No matter how many derivatives I take of e to the x, I'm always going to get e to the x. So this is a nice one to use because it's pretty simple. Okay, that's the first step. The second step is right next to it, like in a little column like I have here. And I wouldn't write 1 or 2 on the AP exam, but I'm just trying to show you that this is step 1, take all the derivatives. Step 2, now we're going to evaluate them at the center. What's the center? It's Mclaren, so the center is going to be 0. So I'm going to evaluate f of 0, which is just e to the 0 or 1. And if I plug a 0 in here, I get e to the 0, which is 1. And f double prime of 0 is still e to the 0, which is 1. And the third derivative at 0 is e to the 0. So the nice thing is that when I plug in a 0, I get a 1 out, okay, every single time. So now let's find the polynomials. What they want here is p sub naught. Well, p sub naught, remember, has to match our original function. All right, so what I'm trying to say here is that the 0th degree polynomial is equal to f of 0, which is just 1. If I want the first degree polynomial, well, that's equal to f of 0 plus f prime of 0. Well, f of 0 was 1, and f prime of 0 times x, is f prime of 0 is 1, so 1 times x is x. So you get 1 plus x. Is that okay? Because remember, I'm just generating the terms of the polynomial now. The coefficients here are done. They're easy. Okay, well, I guess I'll take that as a sure, everything's great. All right, p sub 2, my second degree polynomial, well, that's f of 0 plus f prime of 0 times x plus f double prime of 0 x squared over 2 factorial, because that's the third term in my Taylor polynomial. Okay, so once again, my Mclaren. So again, Taylor, Mclaren, we use them interchangeably. But remember that this is what you need to know. I know the term after this is going to be f triple prime of c times, well, all right, we'll use 0 for right now. F triple prime of 0 times x cubed over 3 factorial. I know the term after that is going to be the fourth derivative of x at 0, x to the fourth over 4 factorial. They all match, right? That's the importance of the pattern. So if I want the second degree polynomial, well, it's f of 0 plus f prime of 0 times x plus f double prime of 0 x squared over 2 factorial, because that's what the formula dictates. Oh, you can't see it, but I got to do something about the legs of this computer. Ah, there it is. Okay. So see, that's the next term. So I already know these two. It's 1 plus x. And all I have to do is figure out this one, this piece here, and add it to it. Well, what's f double prime of 0? It's 1, right? And so it's just 1 times x squared over 2 factorial. Well, 2 factorial is 2, so it's 1/2 x squared. And for the third one, well, that's equal to f of 0. So, f of 0 plus f prime of 0 times x plus f double prime of 0 x squared over 2 factorial plus f triple prime of 0 x cubed over 3 factorial, right? So you notice that this power is matching the degree. Sorry. Very sorry. This power here matches the degree of the polynomial. So what I'm doing is I'm saying, well, I already know these two, so I'm just going to put that in. And I just found this one, so I'm going to add that to it. And now I just have to add, I'm sorry, I went on the wrong one. Sorry, scratch that. We were working on, I think we were working on the second. No, we worked on the second one. My bad. We're on the third one now. So I just have to find this piece. Well, what's f triple prime of 0? F triple prime of 0 is 1. So it's 1 times x cubed over 3 factorial, or 3 factorial 6. So it's x cubed over 6. And if I go on to the nth, then what I'm going to have is 1 plus x. I'm going to have all the stuff we just computed or just found plus dot, dot, dot. And now if I plug, again, I have to do the nth derivative at 0. So if I plug that in, I get a 1 times x to the n over n factorial. Okay, so this is the nth degree polynomial that approximates e to the x. Okay, and again, what I mean when I say that is, if I put all of these functions into my calculator, so here's the original function, e to the x. Here's the first derivative, the constant. Here's the first derivative. Here's the second derivative. Remember, our center's at 0. Here comes the third derivative, or the third degree polynomial. They're all derivatives. What you notice is, say, from negative to positive 1/2, and let's see if I can trace at 0, and let's zoom in a little bit more if that's possible. But the idea is that the higher up we go, or the more terms we have in our polynomial, the better the approximation is going to be. If you look really, really close, so between negative and positive 1/2, these curves are really taking on the same values as the function is in that small little interval. And furthermore, if you look in your table, here we go, where x is equal to 0, you notice all the output values, they're all 1, and we know e to the 0 is 1. So it's given us stellar approximation of the function e to the x. All of them are centered at x is equal to 0, say between positive and negative 1/2. Now the further out I move away, so let me just shut off a couple. Let me shut this one off, this one off. Oh no, let's leave this one on, and let's shut these other polynomials off. So I'm just going to leave the tangent line there to show you that really, really close to x equals to 0, it's like dead on. It's a really good approximation. If I move further away from center, the approximation gets worse and worse. So the idea is that we're going to take these simple little polynomials that we can generate by hand and use them to approximate a function. In this case, it was e to the x. Are we good, you guys? I need some kind of feedback. Anybody? Anything? You're probably all playing video games. When they ask to see my chats for participation, and there's no participation, and they can hear me on the video asking for participation, and there's no participation, then there's going to be problems when it comes to grading. All right, good. See, I have to threaten you with grades, but it's true. They, like Mr. Scurry, if you can get into ESB, he's showing as a teacher now in our ESB because he's the math guy if we have any trouble with the children. All right, anyway, sine of x, okay? Our function sine of x, they want us to find a 7th degree Mclaren polynomial. Good, I know my center 0. So we had done this one in class, okay? We write down the original function. The first derivative is the cosine, second derivative is the negative sine, third derivative is the negative cosine, the fourth derivative, we start back, this recycles, right? So after every fourth derivative, we just go right back through the list again. So the fifth derivative, we would expect it to be this one, the sixth derivative, this one, and the seventh derivative, this one, okay? So the sine, what you know is after at the fourth derivative, it cycles back to the beginning. So, you can just take the first 3 if you want, or 4 from the beginning, and use that to cycle back so you don't have to keep taking the derivatives. Anyway, if I evaluate all of these derivatives at 0 because it's Mclaren, well, the sine of 0 is 0, the cosine of 0 is 1, the negative sine of 0 is 0, the negative cosine of 0 is negative 1, sine's 0, cosine is 1, 0, negative 1. So we notice a couple of things. We notice we're bouncing between 0, 1, 0, -1. We notice that the signs are alternating. That doesn't matter. Okay, let's build the polynomial. Let's write the 7th degree polynomial that represents the sign or that approximates the sign. So remember, the first term is f of 0. Well, f of 0 was 0. So normally we wouldn't write this in here, but I'm just doing it for demonstrative purposes. Okay, plus, right? Then this is f prime of 0 times x. Well, f prime of 0 is 1, so 1 times x is x. The next one is f double prime of 0 times x squared over 2 factorial. Why? Because this power has to match that factorial. Well, that's going to become a 0 anyway, so that's what we get. We're good. Okay. The next one plus, well, for the 3rd degree, so this is going to be f triple prime of 0, which is -1, times x cubed over 3 factorial. So I get negative that thing. The next one, the 4th derivative of f at 0 is 0, so it's 0 times x to the 4th over 4 factorial, plus 1 x to the 5 over 5 factorial, plus 0 x to the 6 over 6 factorial, minus x to the 7 over 7 factorial. And what's nice is that all of these zeroed terms are going to go away. And we write what's left. What's left is x minus x cubed over 3 factorial plus x to the 5th over 5. So all the odd powers of x, which makes sense because sine is an odd function. And so this 7th degree polynomial would give us a really good approximation of the function sine of x at the point where x is equal to 0. Similarly, we're going to do that with the cosine. Okay, so the cosine cycles too, just like the sine, as you would imagine. I start off with the original function. They want a 6th degree Mclaren. So I'm going to take 6 derivatives. So here's the original, 1st derivative, 2nd, 3rd, 4th, ... Okay, it's Mclaren, so I have to evaluate all of these f values at 0. So I went ahead and did that. And again, it looks strikingly similar to the sine, but you all know that they're the same, right, except for that phase shift of pi over 2. Anyway, so now we have to build our polynomial. So remember, the polynomial Pn of x is equal to f of 0 plus f prime of 0 x to the 1st over 1 factorial, if you will, plus f double prime of 0 times x squared over 2 factorial, plus f triple prime of 0 x cubed over 3 factorial. So all I'm doing is building up the terms of this polynomial. So f of 0 was 1. I'm plugging it in for this. Okay, plus 0x over 1 factorial, or 0 times x, because 1 factorial is 1. So generally we don't write that. So we get 0 times x plus -1x squared over 2 factorial plus 0x cubed over 3 factorial plus 1x cubed over x fourth over 4 factorial plus 0x to the 5th over 5 factorial minus x to the 6th over 6 factorial. And again, in this case, the odd terms cancel. And what we're left with is all the even terms, because the cosine's an even function. So we're left with the even powers of the cosine. So we write the polynomial, the 5th degree polynomial is given here. Okay? It's cute stuff. So e to the x, sine of x, cosine x, those are the 3 basic ones. Let's look at when the center is different. Okay, so now we're talking about Taylor. It's the same formula, okay? Same as the Mclaren polynomial. We had f of 0, f prime of 0 times x to the 1, f double prime of 0 times x squared over 2 factorial. Now that we're going to have a different center, we're going to put x minus c in all of those, okay? And what we want to do is we're going to find these polynomials here, p sub 1, p sub 2, and p sub 3. these Taylor polynomials for the sign of x centered at pi over 3. Okay, so now we have a different center. Thankfully, which is why this is so important, we know what the sign of x is approximately equal to. We know we start with an x, we alternate the signs, and we only include the odd powers. And whatever the power is, the factorial underneath is going to be the same, right? So I'm going to throw a few more terms on here. So it's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. The next one would be minus because the signs alternate. So I would expect this to be x to the 7 over 7 factorial plus x to the 9th over 9 factorial, x to the 11th over 11 factorial, dot, dot, dot. I don't need that many, but I'm just showing you that's how easy, if you know the formula for the sign, and you need to know that, then you can generate these things very, very quickly. So I write down the original, and I take 3 derivatives, okay, because I want P1, P2, P3. And now I'm going to be evaluating f and its derivatives at pi over 3. So rather than plugging in 0 here, I'm plugging in pi over 3. So when I do that, you have to remember your unit circle, and generally AP will only give you problems that come from the unit circle to do without a calculator. So remember that the sign of pi over 3 is root 3 over 2. Pi over 6, it's 1/2. Pi over 3, it's root 3 over 2. The cosine of pi over 3 is 1/2. Okay, the second derivative, the negative sign of pi over 3, well, it's 3 pi over 2, but now it's negative because that would be in quadrant 2, right? And the third derivative of pi over 3, so now we've got the negative cosine. Well, the cosine is 1/2, but if we attach or multiply this negative to it, we get negative 1/2. So now let's build our polynomials. A first degree polynomial is going to be f of pi over 3 plus f prime pi over 3 times x minus pi over 3. I'm done. Well, almost. I got to be a little more specific. So f of pi over 3 is root 3 over 2. So I'm replacing that with this, plus f prime of pi over 3. So remember, this is the coefficient part. It's 1/2 times x minus pi over 3. Okay. The next polynomial is the second degree polynomial. So it's this term plus the second. So again, this degree is going to match the derivative number. Okay. So I already know what these are because we just found them above. So I just need to go up one more term. Well, f double prime of pi over 3 we found is negative root 3 over 2. Now, remember that this is going to be x squared over 2 factorial. So what I did was I just moved this 2 factorial over here. Just to remind you that this whole thing is a coefficient. This is x to the something. Okay, so x minus 3 squared. And 2 factorial is 2 times 2 gives me 4. So to clean it up nicely for AP, this is it right here. And for the third degree polynomial, well, we already found this term and this term. We just found that term, and now we've got to find this one. Well, you know, this is going to be x. This one's going to be x cubed. Since I have a center other than 0, I know it's going to be x minus center cubed. I just have to figure out what this is here and then combine it with this factorial. So this is negative 1/2. Remember that 3 factorial is 6. So 1/2 times 1/6 is 1/12. So I left it there. So I brought all this stuff down. I replaced this piece with negative 1/2 times this over 3 factorial, and then I combined it at the end. So it's really quite simple. I'm not sure how they're going to do the FRQs now. They said they were going to have more to come on, like, I want to say April 6th, maybe. I don't know off the top of my head, but probably in another week or two, they're going to give us a little bit more information as to how that 45-minute FRQ is going to work. So as soon as I get the information in, I will post it on EDSB and let you guys know. The Because, yeah, apparently AP has given tests under special circumstances like that before. It's just none of the teachers have ever experienced working with what they would pose to you in a test like that. So we don't know the formatting or anything like that. I'm sure the format's going to be similar, but, I don't know if they're going to start with a simple problem and build all the way up to, Taylor polynomials, let's say, or if it's going to be like totally randomized questions. Yes, I have the information about the exams that they posted, that it's going to be a 45-minute FRQ that you'll take under a secure server to prevent cheating. But as far as like the actual formatting and question types, if you look at enough, remember in AB last year, you guys probably did a whole bunch of FRQs for practice, and you noticed a pattern, right, that they always asked. They always gave you like a region, right, bounded by some curves, and first you had to find the area, and then you had to spin it around the x-axis and find the volume, and then da-da-da-da-da, right? So I don't know if it's going to be similar to that, or if it's going to be completely like off the wall. So that's what we're waiting to see. And as soon as I find out, trust me, I will let you know, and I will start you practicing toward that format that they're going to let out, if they let it out. Who knows? Okay. So, quick recap. What you need to know is that if you're asked to produce a polynomial approximation for e to the x, that right away you can just say, hey, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x fourth over 4 factorial plus x to the 10th over 10 factorial plus x to the 954 over 954 factorial all the way to x to the n over n factorial, right? This is really important that you know this by heart. And what this produces, if you look at the pattern, this is just x to the n, right, over n factorial. So this matches this. This can be written in the same way. And the reason why this general term is important is because if you know this, then you can just spew off any terms you need to approximate e to the x. Now, I don't know to what extent they're going to use this, because we're talking about power series, and they're leaving power series out of the curriculum now. So more to come on that. Know it anyway. It's not that hard. You can kind of see that pattern, how, for every term, I'm just adding 1 to the exponent and dividing by the same exponent. That's the pattern here. The sign of x, you should be able to spew all of this off, in its general term. Since it's alternating, we get negative 1 to the n. And then this is to get these odd powers only. This is x to the 2n plus 1. And guess what? Whatever this exponent is, you're dividing by that factorial. So that's kind of nice. For the cosine, those are the even powers, again alternating, so we're going to have this negative 1 to the n. And we want the even powers, so we can write this as x to the 2 times n. If n is 1, then we have 2. If n is 2, then our power is 4, and so forth. And guess what? This matches what's down here, except this has a factorial. So what I want you to try as part of your homework is, I think we did this one in class, so it might be my bad. I want you to try and generate a Mclaren polynomial for this function here, 1 over 1 minus x, because this is a frequent function. This one's not so frequent, but I wouldn't be surprised if it popped up, because AP is very adamant about the arctangent for some reason. And I even put hints down here. I'm giving you the general term, so you can generate all the terms you want to very easily for both of them, okay? The question is, what goes in the middle? So just like I have up here, I started, here's the function, here's a few, I generated a few terms of the polynomial, and noticing the pattern, I get this general term. The question is, can you come up with the stuff in between? Can you do it? Can you do it from scratch and sort of see the relationship between this general term and your polynomial? Okay, these are the ones you have to know by heart, and in the next class I will actually make sure to go over these so that way you have them okay. But if you know these right here, these guys right here, these general terms, you don't have to generate. You don't have to sit there and rack your brain going, oh, am I on the third derivative, the fourth derivative? Just start, when n is 0, you got x to the 0, right? Plus when n is 1, you get x to the 1, plus x squared, plus x cubed, plus da-da-da. Well, I just filled that blank in for you, didn't I? You see how easy that is? So if you know these general terms, all 5 of them, 1, 2, 3, 4, 5, if you just know those, if you can just memorize those, it's gonna be a cakewalk. I just wanted to show you where it came from. Here's one last one with a center at c equals to 1, and then I'll stop and give you guys the rest of your time to yourself, because I know you have other things to do too. Our function's ln x, our center's 1, and we want to find p sub 1, 2, 3, and 4. I start off with the original function, ln x, and I'm going to take 4 derivatives because I need a 4th degree polynomial eventually. So first derivative is 1 over x, but what I'm going to suggest is that you write that as x to the minus 1. Why? Because you're going to have to take a second derivative, and it's easier to take the derivative in this form than it is in that form. So if I leave this alone, and I take the second derivative, then I can use power rule, right? Negative 1 x to the minus 2. And I'm rewriting it in a simplified form for a reason. Oops. Again, I want to leave it in this form because now I want another derivative, so that's going to make that a positive 2x to the minus 3. Oh, I forgot my 4th. I did the first 3. I forgot the 4th one. So I guess over to the side, if I did f4 of x, so the 4th derivative would be negative 6x to the negative 4, which is 6 over x to the 4th. And if I evaluate that 4th derivative at 1, well, it's going to be 6, right? Whoa. So anyway, let's put it together. The degree 1 polynomial is f of 1. So remember, I got to get it x as far as till its degree matches this degree, right? I need x to the first power. Since we're centered at 1, we're going to use that formula x minus c. So it's f prime of 1 times x minus 1 over 1 factorial. Well, we found that f of 1, that's a 1, is 0, plus, now f prime of 1 is 1, so it's just 1 times x minus 1. So we have this quantity. The second degree polynomial, well, we know that it's p sub 1 plus the next term up, p sub 2. This is p sub 1. And now we're going to find p sub 2. Well, what's p sub 2? That's the second derivative evaluated at 1, which is negative 1 over 2 factorial. So I would just put negative 1/2 times x minus c squared. Right? The third, well, it's p sub 1 plus p sub 2 plus the next term up. Okay, so here's my p sub 1. Here's my p sub 2 plus p sub 3. Well, what's the third derivative of 1? It's 2 times x minus 1 cubed over 3 factorial. Well, 3 factorial is 6. So just working on this one term here, I've got 2 times x minus 1 cubed over 6, and all I did was divide in to get this term. And that's it. That's how you write a Mclaren or Taylor polynomial to approximate any function. It's really quite simple. So the homework that's on WebAssign, that's for you to get some more practice in. I think a lot of the problems are sort of like these, where they want you to find, a 5th degree, a 4th degree, that kind of thing. So give that a whirl. We'll see how you do. And if there aren't any more questions, then I'll end the live stream. So go ahead, ask away if you have them. Speak now or forever hold your peace. Anybody, anything? There is a general power series for ln x, and I believe I talked about it in class. But I don't want to incorporate that in here. So you're looking for the general term, right? Is that what you mean? The general term? So here's some fun for you. Look at the pattern and try and come up with it. You'll probably find it on Google, but try not to look at Google because you're smart. Try and look at the pattern. What's happening with the powers? Let's see, this is x to the n, right? Because we're adding 1 for every term we go up, and we're still dividing by that factorial that matches that power. I wonder if we could come up with a general rule or a general term. I think you could do it. So try it, and we'll discuss it next time at the start of class. Anything else? Anybody? Bueller? Hang on. You guys are killing me. Okay, well, I guess I'm going to say have a great day, and I'll talk to you on Wednesday. If you have any questions in the meantime, if you get stuck on the homework or whatever, you can reach me through Remind. Edsby has been down. It's been really bad today. Not the best platform, in my humble opinion. So, probably the best way to get in touch with me is through Remind. So just send me a Remind message and say, hey, I don't understand how to do number 4 in the homework or whatever. And I'll make a quick video and record it and post it for you with all the step-by-steps and the explanations. Okay, you guys have a great rest of your day, and I'll see you Wednesday.